Beautiful. Okay, so today is a little bit out of source because we have a large number of visitors from my fourth block, AV Physics class. Woo! Okay. Yeah, this is a completely different dynamic than what you guys are used to. Okay. Normally there's just the 6 groups of merely physics students. Okay, so let's talk about some things that I've got your guys' labs graded. I'll try and get this back to you. I just haven't recorded them in the grade book. But among the long list of things that annoy me, and some of you use this in your questions, like, you know, what would happen if you go to the moon, or what would happen if you use a stiffer spring? There's 2 words that you are absolutely forbidden from using, or at least it just greatly annoys me. And mainly because the English language has more words than about any other language. Change and different, okay? If you feel the urge to write those in a question when you're trying to answer it, oh, it's going to be different. Oh, it's going to change. No, horrible, stop, okay? It's too vague. If you say, well, you know, what would happen if you used a stiffer spring and then you put that mass on it? You go, well, the slope is going to change, or the elongation is going to change. Okay? This is not a political campaign. I'm running on change. No, be specific. Is it going to increase? Is it going to decrease? Okay? Or it's going to be different. No, stop. So if you're writing out an explanation, and you're going to write out a lot of them, and I say, hey, what would happen if we increase the gravitational field or decrease the gravitational field? Whatever you do, just don't write, say, oh, it's going to be different. No, stop, bam, horrible, don't. Okay. All right, now that I'm done with that tirade. So let's talk about this process of dimensional analysis, okay? Listen to me. Dimensional analysis is a process. It is not waving the magic physics wand and hoping something happens and then, oh, it's a miracle, all right? Having done this for a long time, and basically I kind of teach you guys how I learned, okay? And I teach you the thought process that I go through. So this process of dimensional analysis is one of the most vital skills that you're going to have. And you can use it in chemistry, you can use it in physics, you can use it in economics, okay? Because, again, so often you all are so wrapped up in writing down numbers and plugging that into a calculator and hoping the oracle speaks to you and gives you the right answer. And then you go back and you read the question and go, oh, Burkamp wants a velocity. Okay, well, I'll put meters per second on the end of it. Or Burkamp wants a force, I'll put newtons on it. But it's like, but then you have all these numbers written down with absolutely no units, and then like a miracle happens, and then, oh, it turns into a force. If you're really going to understand anything, physics, chemistry, economics, you have to be able to go beyond the numbers. Not just, oh, hey, I wrote down numbers, I plugged them into a calculator, and I got a numeric answer. What does that numeric answer mean? I don't know. This is what the oracle said. I'll write it down. I'll put units on the end of it. You're missing the big picture. You are going to make so many stupid mistakes because you're going to write down numbers. Like, for example, you're going to try and add, 5 and 12, and in reality, what you tried to add was 5 seconds and 12 meters. And it's like, whoa, wow, you added time to a distance. But you don't realize that if all you write down is 5 and 12, okay? The biggest thing you have to understand, when I grade your papers, and I spent a lot of time last night going through these labs, is that I am just, if not more concerned about the process than I am the product. It's like, yeah, am I worried about the correct answer? Yes. I'm also very, very more importantly concerned about the process. Once we get into these more and more complex problems, if all you do is just write down an answer, bad things are going to happen. I will have an absolute conniption fit, okay? I want to see how you got it. And I'm not doing that to be a jerk, okay? I'm not. I'm not like, oh, Brickham's just a jerk. No. I know what the world is going to demand of you, okay? The world is not going to demand a simple answer that you're going to type in the screen. The world is going to demand of you, hey, can you think through complex situations? Can you articulate that thought process to others? Can you analyze what went wrong? That's the skill set that you have to have. No one, like I told you before, no one is going to pay you $80,000 to sit in a cubicle and punch numbers into a calculator. It is not going to happen, okay? You have to understand what the numbers mean. All right, so let's talk about some of these. Like let's say, for example, on number 8, okay, on that back side where you have v equals the square root of v naught squared plus 2ax. So this is kind of the level of work that I want to see, okay? So this is a bigger equation. The actual equation itself is v squared equals v naught squared plus 2ax. Later on you'll see where that equation comes from. This is what's known as that equation. It's the only equation that has a specific name. This is the only one that is known as that equation. It started with a guy, I don't know, maybe 15 years ago, Nettie, who sat right back there on the back row. And he goes, let's just call it that equation. And I said, okay, cool. And so it's just stuck with that, all right? So v squared equals v naught squared plus 2ax is it's the only one that has a name. And that's that equation. So if I say, hey, we're going to use that equation, this is the one that we're talking about. So a couple of things that potentially can go wrong. For those of you that are math nerds, which is about everybody in this room, could I do this? Could I go, oh, well, the square root of v naught squared is just v naught, and then I'll put that as the square root of 2ax. Can I do that? Okay, then you shake your head no. Why?
Well, because they're one term, like underneath the square root. I don't know. If that makes sense. Not really.
You're kind of right.
Yeah.
Could I do the square root of 2 times the square root of ax?
No.
Could I do that?
No.
Yes, because they are rhymes with multiplied. Multiplied. So you can separate square roots of things that are multiplied. You can't separate things underneath a radical that are just being added together, okay? So you cannot do that, okay? So I'm going to nip this in the bud. And we're going to deal with this equation a lot. So you just can't separate that out because it's going to be added together. Okay. So, Louise, are we going to worry about the 2? Why not?
It doesn't really matter.
Why not? It's 2. It's an important number. Man, don't be distant on the 2.
I mean, it's because we're focusing on the variable, aren't we?
Focusing on what?
The variables?
Yeah, well, the units. Okay. So when you multiply by 2 in this process of dimensional analysis, just multiplying by 2 doesn't change the units. Is it important mathematically when we plug in the numbers? Absolutely. Does it make any difference when you're doing dimensional analysis? No. So this is what I would want to see. I got meters per second squared plus meters per second squared times meters, because x is just going to be some distance. So then you can sit here and go, okay, hey, that's meters squared over second squared, meters squared over second squared. Now I realize that those are the same units, and now I can add them together. Okay, that's cool. And so then I get the square root of meters squared over second squared, and that's just meters per second. That matches up with what velocity is measured in. It's a valid equation. Okay, so this is the step-by-step process that I want to see when you do dimensional analysis. Okay, any questions from anybody on that purple sheet? Isaac, talk to me.
Can you work on number 9?
I can work on number 9. So on number 9, you have 2 pi times the square root of L over G. This is actually a very, very important equation. And you think, well, what's so important about that? So, number 1, this is the period of the pendulum, okay? Tells you how long it takes to go back and forth. And later on, you'll see where this happens. in terms of like when we get into gravitational fields and things like that. If you can figure out what the gravitational acceleration is like on the moon or the earth, and you know the size of the planet, you can actually find the mass of the planet, okay? So one of the things that they did actually when we went to the moon is we took a pendulum, okay? And we figured out what the gravitational acceleration was on the moon. We didn't actually know the mass of the moon when we landed on the moon. We had a vague idea, but we didn't know the actual number. So if you can set up a pendulum, and literally this is what they did. They measured how long it took for the pendulum to swing back and forth. They knew the length of the pendulum. They were able to solve for gravitational acceleration. We knew the size of the moon. From that, we figured out the mass of the moon, okay? Because when you find like the mass of planets and things, it isn't like we can look at the moon on a telescope and there's a little plate that says, oh, manufactured on such and such date, here's the mass, here's the composition, okay? We have to figure that out indirectly. So, here's the thing. When you see uppercase T versus lowercase t, lowercase t means it's like a singular event, okay? How long does it take for Galvin to run 10 meters, okay? That's a singular event. Uppercase T is something that comes back to that same point. Could be the orbit of the moon, could be a period of a pendulum, could be an oscillating spring that goes back and forth. It's something that repeats its nature. So, but no matter what, they're both measured in seconds. Okay, so if this works, that should be in seconds. Is the 2 pi going to alter the dimensions? Nope, don't worry about it, it's important, just not part of the story. So then you have L. So Isaac, this is going to be the length of the pendulum. What's that going to be measured in?
Meters.
Meters. Okay, so I got meters. G is my gravitational acceleration. On Earth, that's 9.8 meters per second squared. So any acceleration, Isaac, is measured in what units?
Accelerate in accelerate. I know it. Kilometers. No.
How about
No.
meters per?
Second squared.
Bingo. There you go. Now, this is what I would do. Okay, if I were working this problem, I would not divide by meters per second squared. What I would do is I would rewrite this as a second step and take meters and multiply it by that reciprocal of second squared over meters. That's what I would do. Okay? So then you've got, oh, okay, well that's the square root of meters times second squared over meters. The meters cancel out. I get the square root of second squared. Winner, winner, chicken dinner. That seconds the equation is valid. Okay? All right, we good? Going once, going twice. So get that purple sheet handed into either the first tray, the first block, or that third tray down if you're visiting from my fourth block. Isaac, you can take my phone and throw it up there like number 2. Craziness of life this morning. Okay, so what we're going to do today is work through that, and I know Bill was disappointed in the fact that it was boring on a white piece of paper. I'll do better, okay? That assignment from what I gave you all yesterday where you had to draw the graphs. So, we're going to spend a lot of time drawing graphs. And at the front page of that is basically showing you, hey, here's the 3 types of graphs that you're going to experience most often. Straight linear function, an inverse function, and then a quadratic, okay? Those are the big 3. Sometimes we'll deal with square root functions, that's pretty rare, but for the most part, 90% of the graphs we're going to do are going to be one of these 3, okay? So the first graph that you drew force and acceleration. So we got the little marble launcher, and so this is kind of a simple example of that. I apply a little bit of force, I get a little bit of acceleration. I apply a lot of force, whoa, incoming. I get a lot of acceleration. So, well done, thank you. So, and again, here's the story. This is the mindset I have to get you out of. You're gonna find the slope of the line, and you all can mathematically find the slope of the line, okay? Rise over run, changing y over changing x, however you wanna think about it, okay? You can do that. I'm not worried about that process. My concern is that you have to be able to understand that slopes have physical quantities. They represent things. And that's something new, okay? You all are just used to finding a number. You've never had to worry about, oh, what units are the slope measured in? So, why did we put force on the x-axis?
Just the independent variable.
That's my independent variable, okay? I control how much force I apply. Do I apply little force? Do I apply a lot of force? Okay? And my acceleration is dependent upon that amount of force. So that's how we plotted that one. So you should have this graph drawn. So we basically answered questions 2 and 3 on the front. Okay? What's the independent variable? Notice I say explain. Okay? On almost every question that I give you, I'm going to say, hey, explain at the end. All right? So when in doubt, just explain it. Now, based upon the graph, what type of relationship exists? And I say be specific in your answer. So just don't say like it's a direct relationship. Mainly because of the fact direct relationships tend to be vague. It's like, is it a direct quadratic relationship? Is it a direct linear relationship? Okay? Just to say it's a direct relationship is too nebulous, okay? So what you want to say, because this is very much a linear function, okay? So you could say, hey, it's a direct linear relationship, okay? If you really want to get fancy, you could say force changes as a linear function of acceleration, or acceleration changes as a linear function of force. Main point here is to say, hey, it's a linear function. Now, we're going to work number 6, because you need to think through what's going to happen on number 6 when we do dimensional analysis. And notice I say, using dimensional analysis below, determine the physical quantity represented by the slope. I want to see this process. Now, we're going to do it, okay, because I want everybody to make sure we're cool on what's going to happen here. So, again, I'm not worried about the numbers. I'll worry about the numbers later. All I'm worried about are the units. So, I got change in y over change in x. So my y-axis is in meters per second squared. Now my x-axis, I can either put newtons or kilograms meters per second squared. I'm going to go with the kilograms meters per second squared option because on my x, or on my y-axis, that's in meters per second squared. So I want to come down here and go, okay, hey, that's kilograms meters per second squared. Cool. Those are going to cancel out. Now, what do I have left? Kilograms or 1 over kilograms?
1 over kilograms.
1 over kilograms. Okay? Now, momentarily, I want you to all act like this problem doesn't exist. We'll get back to it. For right now, act like that number is not there. Okay? I want you to think through like you're in like an Algebra 2 classroom. Okay? And I'm going to say, hey, here's x. Now, what I want is the inverse of x. So how can you write the inverse of x?
X to the negative 1.
X to the negative 1, that's cool. Or
1 over x.
1 over x. Those are my 2 options. So if you have x, the inverse of x, you can either write it as x to the negative 1 or 1 over x. Cool, right? Got that. Now, if the units of that slope had worked out to be kilograms, okay? This is a huge if. If the slope had units of kilograms, what would the slope represent? Do not make this difficult.
Mass.
Mass, because kilograms measures mass. So if the slope had been kilograms, you would say the slope represents mass. Okay? But it doesn't. It's not kilograms. It's 1 over kilograms. So if kilograms represents mass, 1 over kilogram represents the
Inverse.
inverse of mass. Okay? So when it asks you, hey, what does the slope represent? The slope represents the inverse of mass. Because of the fact that if it had been kilograms, you would say, oh, the slope represents mass. But since it's 1 over kilograms, the slope represents the inverse of mass. Okay? Cool with that? Now, over on page 2, like I said, we're just basically kind of piecemeal this thing together. So, on number 7 now, here's what, I'm going to stop talking for a little bit. You're going to find the slope of the line, okay? Make sure you write down the units because everybody's slope can be a little bit different, okay? So right now, find the slope of the line. Pick the point, show me the work. Stop you on the camera for now.